Hello again. The video today is going to wrap up Chapter 8, and we're going to look at the rest of what we need to learn about hypothesis testing. In the previous video, we went through 3 steps that you did to figure out whether something was significant. The first thing you had to do was think about a level of significance, which was typically given to you in the problem. And what that basically was how willing you were to be wrong when you said that something was significant. The most important part of a hypothesis test was calculating the p-value, which is the actual probability that something happened by chance or the actual probability that you were wrong. And we figured out that you compared those two numbers, and if the p-value was less than the level of significance, if your actual chance of being wrong was less than how willing you were to be wrong, then we said that you had a significant result. Otherwise, it was not significant. So that was the basic steps to any hypothesis test. You figured out what your level of significance was, you calculated a p-value, and you wanted the p-value as small as it could possibly be. It turns out that there's lots of different types of hypothesis tests, but the basic idea of what you do is the same on every one of them. You're just going to go through those 3 steps. And from your point of view, you crank some numbers in the calculator and you figure out what the p-value is, and if it's small, you're good to go for a significant result. So today what we're going to do is look at a bunch of different kinds of z-tests and t-tests, see what they're about and how you do them. Some of the most common kinds of tests we do compare averages of things. You want to see if the current average is more or less than what it used to be, or more or less than what you would expect it should be. And so we're going to look at different ways that we can test the mean. We can test the average of something. The first test we're going to look at is what on your calculator is just called a z-test. It's the very first choice you'll find if you go into the test menu on your calculator. I usually call this a one-sample z-test, and that's because you're comparing the average of one sample with what the average is supposed to be. We do use this test when you either know the standard deviation of the population, or you have a big sample. You might remember from the chapter on estimation that there was a difference between Z and T, and Z was for zoomungous samples, which meant that you had to have at least 30. And again, what you're going to do is go into the test menu on your calculator, Stat Tests, and z-test is the very first choice in there. You're going to want to make sure that stats is highlighted. That was also true on the estimation part. It should be by now on all the tests in your calculator, but if it's not, you need to use the right arrow, go over and highlight stats and hit enter. And you want a screen that looks kind of like what I've got on the right, where it asks you for a bunch of different statistics, which most of the time are given in the problem. The thing that's most important when you do these statistical tests is you've got to know what the different variables stand for. When you go into z-test, the very first thing it's going to ask you for is mu0. It's asking you for an average, for a mean, but what this one is what the average is supposed to be. It's the expected mean. Sometimes it'll be the mean of the whole population, which you might know from like census data. Sometimes it's what the mean's been in the past. Sometimes it's just what you expect it should be, but one way or another, it's the expected mean. Then it asks you for the standard deviation, and that officially means the standard deviation of the population, but it could also be of a big sample. In problems, that's always going to be given to you. The third line down is going to talk about X bar, and that's the actual mean that you have in your sample. You're always going to have two different means, two different averages that come up in problems like this. And again, the mu is what it's supposed to be, the X bar is what it actually is now. The last thing that it asks about is the number in your sample. That, again, either it's going to be given or you just count up how many things there are. On the next to last line on your input screen, it has a line that says something like not equal, less than, greater than. What it's doing is asking you whether the actual mean in your sample seems to be less or more than what you would expect it to be. And in order to get the right answer, you do need to highlight the appropriate choice on there. The first choice is not equal, which you would use if you didn't know at all which way it was supposed to go. But really, you always do in problems you're given, so you look at the information that's there and you highlight either less than or greater than, whichever one applies to your situation. Finally, at the very end, it has a choice of calculate or draw. For everything we're doing in here, just highlight calculate, which you can do just by hitting your down arrow, and then hit enter and you'll come up with your answer that you want. Sometimes people ask me, why is there this choice for draw? Well, if everything is set up correctly on your calculator, it could draw a picture of a little bell curve and show how far out in the tail your data is. There's really not much reason to do that, though. What we're going to care about is the results that you get on the calculate screen, and that's just easier if you hit calculate. So to learn how to do this and all the other tests that we're going to be looking at today, we're going to take a quick look at a sample problem. So this one says a teacher thinks her class is really dumb. And so she gives all 25 students in her class IQ tests, and she finds the class average is 89, which I will tell you is way below average. I actually mentioned when we were first talking about z-scores that if I looked at the IQs of everybody in this class, chances are everybody would be above 100. And 89 is quite a bit below 100, so it is well below average. You might remember from before that the average IQ is supposed to be 100. The standard deviation is 15, and so the question here is her class significantly below average? Are they truly dumb? And it tells us to use alpha equals 0.10 or 10%. In this problem, and pretty much anything you'll see in a book or worksheet or quiz, you're given the information that you need to solve the problem. They told us that the class average was 89. That's the X bar, what the average actually is. We also know that the average is supposed to be 100. That's the mu or mu0 on your calculator. The standard deviation is 15. And the number of people in this woman's class was 25. So all of the variables that we're going to be using, I know ahead of time. Sometimes it's useful in a problem to go through, and what I'll sometimes do is actually write the variable by each of those numbers so I know which one's which. I threw in a step here that you don't necessarily have to do, but I put it here on purpose. And that's because sometimes you may be asked to identify what the hypotheses for a problem are. You don't have to do that on most problems, but you do want to understand what they're asking. Remember that the alternative hypothesis, the one that would say we do have a significant result, basically you look at the question and you make it into a statement. So here it would be, this class really is dumb. The class is significantly dumber than average. For the null hypothesis, I just turn that around and throw the word not in it, so the class is not significantly dumber than average. Now with 89 for an IQ, they're definitely not smarter, but maybe that's about the same as average. That would be what we'd be saying, and any difference was just due to chance. If she tested them again, maybe they'd have a little bit higher answer. You will have a couple of problems on quizzes or tests where I will ask you to identify the hypotheses. And again, you can basically just copy the question, but make it a sentence for the alternative hypothesis, toss in not for the null hypothesis. The problem, it told us to use alpha equals 0.10, so a 10% level of significance. That is pretty typical in a field like education. Remember that I mentioned last time, and I really want to stress, that the more important your research is, the lower you want that number. The other typical values that are used are 5% and 1%. And if you are doing something like medical research, you don't want to be wrong very often. That's why you use 1% or possibly even lower than that. So everything so far was just given in the problem and I sort out what it is. The thing I have to actually do is calculate the p-value. And again, your calculator is going to do that for you, but you need to make sure you put everything in and you put it in the right order. So as I go through here, the first thing it asks me is what the average is supposed to be, mu0. That's 100. Then I need to know the standard deviation. That's sigma, and that's going to end up being 15. We have what the average actually is for this class. That would be the 89. And the number, which is 25. Now, 25 is actually a small sample statistically, but I can do a z-test because I do know that standard deviation for the whole population. It appears that 89 is less than 100. That's why I've got less than highlighted on that not equal, less than, greater than line. Make sure everything is correct and I hit calculate and I get the screen over on the next page, and honestly from our point of view all you really care about on that screen is p. Now, there are other methods of doing hypothesis tests where what you might care about would be the z line on there. But for now, what we're doing is a p-value test, so p is what we care about. I actually purposely chose this problem because in it, the p does go into scientific notation. What it says on the calculator is 1.2289897 e minus 4, which means I've got 1.2289, etc., times 10 to the negative 4th power. Basically, it's saying this is a decimal, and the 1 is the 4th place after the decimal point. That's why what I really have here is 0.00012289897. And again, you're going to see that more than once. In fact, you'll see it 2 or 3 times in the examples we're going to go through today, that you have scientific notation. It pretty much is a dead giveaway that you will have a significant result, because what I do is I compare that p-value with the level of significance, which in this problem was 0.10. It's not too hard to figure out that 0.0001 is less than 0.1. And so, yeah, since this is way less than my level of significance, it is definitely a significant result. Again, what you always want is for the p-value to be smaller than the level of significance. If that happens, you have a significant result. If it doesn't, you don't. Here, we had something that definitely was less than the level of significance. So what that's saying is, yeah, the teacher is right. She really did have a dumb class. We're actually going to take a look at 5 different hypothesis tests today, and z-test is just the first of those. Again, z, what you're really looking at is a bell curve. You're looking at the normal distribution, and officially, if you use a z-test, you need to know some stuff ahead of time. You either need to know the standard deviation of the population, like in the problem we just did, we knew that for IQ, that's always 15. Or the other thing you can have is a large sample that you know comes from something that is close to normally distributed. In the real world, though, it is pretty rare that you do know the standard deviation, and there's a lot of times that you want to use a smaller sample. When that happens, we do end up using t instead of z. Now, you might remember when we did the estimation problems in the last chapter, it was the exact same thing. Z was for big and t was for tiny, where you have small samples. We did use what's officially called the student's t-distribution for estimation, and we're going to use it again for a couple of different kinds of t-tests. You should remember from before that the magic number that divided t and z was 30. If you had something less than 30, it was always a small sample. If it was greater than 30, you had a big sample. Honestly, if it's equal, which it almost never will be, you could use either one and it would work out to be essentially the same number. What we're using is officially called the student's t-distribution. While we're not really going to be using it, there's a table in your book that is right by that z table that we looked at earlier that is called student's t-distribution. Sometimes people will see that and they think, gee, I'm a student. This is the student's t-distribution. It must be something that was designed for students. And I actually mentioned briefly when we did the estimation chapter that actually that's not really true. This happened to be developed back in the 19th century in Ireland by the guy that was the chief brewer for Guinness, and he was trying to work out a way of doing quality control on beer. The guy's name was William Gossett, and he did all the math that goes into the t distribution. The problem is that then he and Guinness had a big falling out, and he got fired. But after he did, Guinness claimed that they had all of the rights to the work that he had done. And to get around that, since he wasn't getting along with his former employer, he actually published all of his work under the pseudonym Student, so that it was all public and Guinness couldn't claim that they had the rights to it. So that's why today we have the student's t-distribution. And we're going to use that t-distribution to do what on your calculator is called a t-test. I will often call it a one-sample t-test, and again, that's because it uses one sample instead of two that we'll talk about later. If you go to one sample t-test on your calculator, you'll find that basically everything works the same as a z-test. We're just going to use it when we have smaller samples. Remember again, the difference between large and small in statistics isn't really all that large. Anything that's 30 or more is considered a large sample. On your calculator, if you have a TI-83 or 84, you're going to go to choice number 2, where it does just say t-test. You can actually look at the other choices there and get a preview of some of the other things we'll be looking at, but right now it's just t-test. And we're going to find that pretty much everything works the same as it does with Z. Here's another typical problem, kind of a stupid one actually. It says an insurance company claims that the average value of a home in Happyville is $135,000. A homeowners group looks at 16 homes and they find that the average value is $122,500. The standard deviation is $5,875. I just made up a bunch of numbers for this problem. It says, is the average cost of homes in Happyville significantly less than the insurance company claims? You know, maybe these people think that they're being charged too much for insurance, so they want to show that their homes aren't actually all that valuable. That might not really be the wisest choice, because then if they make a claim, they're only going to be covered for what they say it's worth, not for what the value might actually be. So, that is what they're saying though, and we're supposed to figure that out using alpha equals 0.05. Again, in most cases, you won't actually have to write these out, but I went through and figured out the hypotheses would be the average cost is significantly less than what the insurance company says, or the average cost isn't significantly less than what the insurance company says. Just like before, the level of significance is given in the problem. Here it says to use alpha equals 0.05. And again, what that means is we would be willing to be wrong 5% of the time if we said this was significant, but it really just happened by chance. So when I go and calculate my p-value, I go to stat, test, and t-test, and again, I just type in the numbers that are in the problem. You do need to be careful of the fact that a t-test is going to ask you things in a little bit different order than the z-test is. I actually personally think the t-test makes more sense. It asks first for what the average is supposed to be. That's why we put in what the insurance company said, $135,000. Then it's what is the average actually in our sample, 122,500. And then it asks for the standard deviation, which was 5875. On the z-test, the standard deviation and the actual average are flipped around and in the other order. And again, you just want to make sure you've got it down in the correct order. N is the number in the sample. Here that was 16, and it does appear that our average was less than what it's supposed to be. You make sure all your numbers are good to go and you hit calculate. Sometimes people will wonder why it is that there's always a little bit of a pause on a t-test when you hit calculate. It's because what's really going on in your calculator is it's basically using like a lookup table that's programmed in there, and it has to go sort through hundreds of different possible numbers that go into a formula rather than having just one possibility, which is what goes on with the z-test. So it does take a little longer, but it still is just a couple seconds, and you'll have the answer that you need. What we care about is the p-value, and once again, this one is in scientific notation. On the p line, it has e minus 7, or 10 to the negative 7th power. That's why what I wrote out here is 6 zeros after the decimal point, and the 7th one is the 1 that it had there, so 0.000000199 and some change. Anytime that you get scientific notation, it is like a dead guarantee that you're going to have a significant result. That's way less than the 5% that we were looking at in this problem for a level of significance. So yeah, we're going to have a significant result. So far we've looked at z-test and t-test. Both of those are used when you're looking at what an average of a sample is and you want to see how that compares with what it's supposed to be. The next thing we're going to take a look at is what's called a two-sample t-test. And if you look at the name of that, it tells you exactly what's going on. What you're going to do is you're going to compare the mean, the average, of two different samples, like men or women, or blacks and whites, or what people's grades were like when we did class face-to-face and what they're like when you do online classes. You look at those two groups and you want to see, is one of them significantly higher than the other one? For now, every time you have to do any hypothesis test, it's going to tell you in the problem which one you need to do. When we get to the very end of the class, one of the last things we'll do is to answer the question, well, what if it didn't? What if you had to figure out which kind of test it was? And again, the dead giveaway on this one is that there's two separate samples. That's what kind of tells you it's a two-sample test. Two-sample t-test is choice number 4 in your menu on the test from the TI-83 or 84. When you go into the two sample t-test, you're going to find that it has a really busy looking menu. It asks you a whole bunch of different questions. Although when you look at what it's asking, most of them are pretty straightforward. It asks for X bar 1, SX1, N1, X bar 2, SX2, and N2. And what they're wanting to know are the mean, the standard deviation, and the number that were in each of the two samples that you have. The things that have ones after them are asking about your first sample. The things that have twos after them are asking about your second sample. And again, in any problem you're doing, that's all going to be given in the problem. You may have to shuffle it around and make sure that you know the right order for the numbers, but you'll know all of that ahead of time. If you hit your down arrow, you'll notice a couple of other questions that are down below all of the variables you have to enter. One of those is going to ask you whether the information is pooled. It has pooled question mark, yes, no. The reason it asks that is that there actually are different formulas that can be used to calculate both t and the p-value that you would have for a result. And it depends on whether your data could be related to each other or not. For our purposes in this class, every problem we're going to do, you want to just choose yes for that. Once you've done that once, it should stay there for every other thing you do after it. It's possible that in future classes you might get into the difference between the formulas you can use and you might have to change that, but for basic stats, yeah, you just always pick yes and that will give you the answers that you need. And so again, we're going to look at another example, and I'll tell you ahead of time that yet again, we're going to get a scientific notation answer for our p-value, but we'll lead in and see what we get with it. It says the Greater Chicagoland Convention and Visitors Bureau did a survey to find the average income of people who visited the city for various reasons. And on this screen, we've got a whole bunch of different numbers. If you look at it, it's all the different things that are going to end up being entered in your calculator. It says a sample of 27 people who attended sports events found the average family income was $87,900 with a standard deviation of 12,970. And a sample of 19 people who attended the theater found that the average income was $127,400 with a standard deviation of 28,950. So I told you before that all those things you have to type in your calculator are going to be given to you in a problem, and here they are. The thing is, though, that you do need to again sort out which number's which when you go through that. Like here, N1 is going to be 27, X bar 1 is going to be 87,900, and SX1 is going to be 12,970. That's not the order that you enter them in, so you do want to make sure that you do know which one's which when you go through. Question here says, do these results indicate that people who attend sports events earn significantly less than those who go to the theater? Use the 0.01 level of significance. Well, the numbers they gave us, 87,900 and 127,400, yeah, it does appear that the first one's less than the second, but we want to know, is it significantly less, or is it just something that happened because they took a couple of small samples when they were doing this? We're going to cut to the chase on this one and just look at what you would do with your calculator. Again, what you want to do is go to sample t-test in the stat tests menu. And we type in all the numbers that were presented in the problem. Again, realizing it's got to be average that comes first, and then standard deviation, and then the number. I go through that with the first sample, and then I go back and I put in those same things for the second sample. Once I get through entering all of those numbers, It asked me that question of less than, greater than, and here what it's asking is, does the first sample appear to be less or more than the second sample? Well, 87,900 is definitely less than 127,400, and what's more, the question was phrased as less. But you do want to look at the order that these are asked in too, and make sure that the first one is here less than the second. Pooled, again, I told you to always put yes down for that one. So we make sure all of that stuff's entered, hit calculate, and again, we got a busy screen, but the only thing that we really care about on that screen is the p-value. That's the thing that matters. And here it did once again go into scientific notation. We're going to do 5 examples, and 4 of the 5 will today. And on this one, it is 6.706439 times 10 to the negative 8th power. And that's why we've got 7 zeros and then 6, 7 after that when I wrote out what that p-value was. Now again, whenever you do have scientific notation, it's not too hard to figure out that that's way less than 1%, and so we will end up saying that this is significant. When you do your comparison, again, you look to see, is the p-value more or less than the level of significance? Here, that number in scientific notation was less than alpha equals 0.01, and because of that, yes, we do have a significant result. Now you may have noticed while you were going through and practicing how to put the numbers in, that right above two-sample t-test, there was another option in your calculator that said two-sample z-test. None of the problems you're going to be asked to do in this class will be that, although theoretically you could do a two-sample z-test in virtually the same way we just did t. The only difference is that if you use two-sample z-test, both of the samples you used would have to be big samples. If either one of them is small, it's automatically a t-test. And pretty much every situation we're going to have in this class will be 2 small samples, or at least 1 small sample. And so that is why it's two-sample t-test that we're going to end up using. There's 2 other tests that we're going to take a look at. The next one will be a real quick look because this is actually what you did in the last video. It's what's called a 1 proportion z-test, and when you do a 1 proportion z-test, what you're looking at is the percentage of something more or less than what you would expect it to be? Is the percent different from what you expect, or is it different from what it's been in the past? Well, if you look through the test menu in your calculator, you might notice that while I was just talking about the difference between z and t-test, there isn't a 1 proportion t-test. There literally is not one. It doesn't exist. And that's because for percents to work, you pretty much have to use the theories that go with z. And anytime that we're looking at percents, at proportions, it's always going to be a z-test that we do. We actually looked at a 1 proportion z-test as our example in the last video, and again it's choice 5 in your calculator. The things it asks are p0, x, and n, and then you have that not equal, less than, greater than line. We're going to put the appropriate stuff in and find out what our answers are. Again, p0 is always what you think that the percent should be, and you put that in as a decimal. X and n are the number that you got in your sample and the total number in your sample. And the important thing there is x is always less than n. It's like how many are the way we're talking about out of how many total. So this time what we're going to look at is an example that comes from baseball. And it says a baseball player has a career batting average of 287, but he seems to be doing worse this year than in the past. So far he has 70 hits in 250 at-bats. Even though we call it a batting average, What a batting average really is a percent. When you say somebody's batting 287, what you really mean is that they get a hit about 29% of the time. And so we're going to see, is 70 hits out of 250 worse than what they've done in the past? The question says, is this significantly lower than normal? And it says use alpha equals 0.01. And again, we go to choice 5 in that test menu. The P0 is what the average has been, which is 287. And again, you got to make sure that decimal point's in there when you enter that. This year, they've got 70 hits in 250 at-bats, and so X and N are those numbers. And the question said, is it lower than normal? That's why we got less than highlighted. You go down to calculate, and again, the thing we care about is P, not P hat, but P. And here that is about 0.403. This time it's not in scientific notation. And what that's basically saying is there's a 40% chance that this is not a significant result. And again, we do our comparison by looking at that p-value, and you compare it to alpha, the level of significance. Here, 0.403 is bigger than 0.01. That's why we say this is not a significant result. The idea is that we would be willing to be wrong 1% of the time. Here, we'd be wrong 40% of the time if we said this was significant. And so really this player is not performing particularly worse than normal. It's probably about the same as he usually performs. And there's one more test that we're going to take a look at today, which is what's called a two-proportion z-test. A two-proportion z-test, the question you're answering is, does one group have a higher percentage of some characteristic than another group does? What's going on when you do a two-proportion z-test is you're comparing two different groups at the same time. You're looking at, for instance, is there a difference between men and women, which is the example we'll look at here in a minute. And so you look at two separate groups rather than seeing, is one group different from what you'd expect it should be. If you go to a TI 83 or 84, this one is going to be choice 6 when you hit stat tests. And again, it is two-prop z-test, two-proportion z-test. So our example for this one is going to go back to the last election. And this is an actual poll that was done before the 2016 election. It says that there was a poll that was taken. They surveyed 820 men, and of those, 525 said that they planned to vote for Donald Trump. But that same poll also surveyed 900 women, and only 270 of them said that they planned to vote for Trump. And the question that we're going to end up answering is there a significant difference in Trump's support between men and women? And we're supposed to use the 10% level of significance, which again is something that's a pretty standard amount to use in a field like politics or social science in general. This test is pretty straightforward. You just need to make sure that you got the right number in the right place. When you go to two-proportion z-test, it asks you for x1, n1, x2, and n2. And what that's saying is what number of men said they'd vote for Trump, how many men did they ask total, what number of women said that they'd vote for Trump, and how many women did they ask total. That's what those first four numbers are. The trickiest line is actually the very last one here, where you have that less than greater than line. And if you're not absolutely certain, what you can do is literally divide out the numbers that you have there. You could figure out what was the percentage of men and what was the percentage of women. Because what it's asking you is the percentage for men less than or greater than what it is for women? And if you do divide this out, you're going to end up finding in this case that there were about 64% of men that said that they would vote for Trump. There were 30% of women that said that they'd vote for Trump. And yes, 64 is a lot more than 46, which is why we're going to choose greater than. The first one is greater than the second. So I highlight that, I go down to calculate, and we look at what our results are. And you'll notice that when you do go to calculate, one of the things it gives you is actually those two numbers I just said. That's what p hat 1 and p hat 2 are just the percent of men and the percent of women that said they'd vote for Trump. The number we care about, though, is above both of those. It's the one line that just says p. And here you have a ridiculously small number. Not only is it in scientific notation, it's 1.188 times 10 to the negative 45th power. I did not bother writing this out with a decimal point because if I did, I'd have to put 44 zeros and then 118852. What that result is basically telling us is that the probability that this just happened by chance was 0. You would have to do this quintillions of times to get that result just by chance. And here it was something that we could say, yeah, there definitely is a significant difference, and Trump's support is significantly higher among men than it is among women. What all of those different tests are doing is asking you whether things have a significant difference. And again, what you always do is you look at the level of significance that's given in the problem, how willing you are to be wrong. You use the numbers you know to calculate a p-value, which is what the actual chance you're wrong might be. And if that p-value is less than the level of significance, then you have a significant result. For an assignment, you're going to be looking at a bunch of different hypothesis tests, and when you get to the next quiz, what's going to happen is you will have basically one example of everything, and you want to be able to answer some questions about it and calculate what the results are. So that's what we've got for Chapter 8 for hypothesis tests. Hopefully that was fairly clear going through it. Again, it's crank some numbers out in your calculator and see what your results end up being. Good luck with that, and we hope that you guys all do have a good week.